So continue working on the basics today, just Verilog syntax and everything. So if you open up the basics tutorial, you'll see the details. And we were at the three different modeling methods. There are a couple of things to cover as well. If you look at the in class number 2. So as we said, initial statement will only be executed once, right? So it sends the initial values, and that's it. So it moves on. If you have an always block after it, it will move on to the always block, and these will run all the time. So it's different from the C language. If you have, most of you have learned C++ and everything, similar to that. So all these instructions as a software or the embedded systems, they were stored in the instruction memory. So the pointer will access every single line and execute it. But for hardware, it's different. So there's one thing that you guys have to shift your mind on, which is hardware discrete language compared to the software, the coding, assembly or C, doesn't matter, stored in the instruction memory. So after this is being executed, it's being synthesized on the hardware. Right? It's not like running from top to bottom. This is hardware, it's not software. So after this is synthesized and implemented on the FPGA or maybe on the chip eventually, it's already a hardware. So the question here is, how could that be possible? A hardware could be executed forever, like this. And the initial begin, these are mostly in the simulations. So Verilog, we run Verilog simulations. So you can see the waveforms in the simulator as what we did in the lab yesterday, right? You see the AND gate logic. But also there's a difference between synthesizable and not synthesizable Verilog. So synthesize means it converts your Verilog into a net list, which is used for hardware design. So some of them are synthesizable. If you are targeting for a chip, okay, you're targeting for a chip, you have to make sure that your Verilog is synthesizable, okay? Sometimes it runs in Vivado as a simulation. Sometimes it just doesn't work if you want to synthesize it into hardware. So which means if you use it in Cadence, right? In Cadence you are programming. So also you can program. Remember in the VLSI you didn't take it, but for other people you took Cadence, all the tutorials. Remember at the very beginning the counter design for Genus, right? For Genus. The counter design for one of the tutorials is a counter design is actually a Verilog code, and you synthesize that in Genus, and then in Innovus, you load all the netlist files and all the technology files into Innovus, and then convert everything to a layout. But at the very first step was a netlist. Let me just draw it here, just in case. It's easy to get confused actually. If you're targeting for a chip, right? So start with RTL. So RTL is very similar. It's almost the same as just all the Verilog code we're learning this class. It's a register transistor level hardware description language. It's also Verilog, but you are modeling the different components in the different level. But it's just Verilog, to make it simple. So. And this has to be synthesizable. And then this one is converted into a net list by Genus. Right? And then it goes to it being loaded to Innovus, right? With all these other tech files for TSMC, and from Innovus we convert it into a layout. So that's the workflow for making an ASIC chip. So for FPGA, it's going to be very similar process It's going to be very similar. Just copy everything over here. And if you want to implement it on the IPGA, it has to be synthesizable, even though IPGA is not an ASIC chip. It's not, but it's also a hardware. Okay, it has to be synthesizable, which means whatever you write in the Verilog, code, it has to be something physically can be represented on the hardware. Okay, however, for Vivado, simulation, it doesn't have to be synthesizable. You write up Verilog code, it's very it has a high level tolerance, whatever you even sometimes there are syntax errors, it's still able to go through and show you the simulation results. But however, that code, all these Verilog here, probably cannot be used for hardware design, like IPGA or ASIC. Okay, so for the ones we have over here, I mean, a lot of times some of the platforms doesn't take initial begin. These are just for simulations. I mean, not really for hardware. And also there are very tiny differences between the synthesizable, non-synthesizable always blocks, and very little differences about the syntax. So whenever the tool report errors and you notice it, then just make notes on that. So you know that, hey, this is not synthesizable. In the future, we just don't use it. So that's the concept over here. So you can see, let's come back to my original question. So like we said, right? So the always block will be executed forever. As a hardware design, whenever this is being synthesized in the hardware and being implemented on the hardware, how are you able to execute a piece of hardware forever? And how that works? Think about it. I mean, as a hardware, how could you come back and rerun it from the top? Right? For the software instructions, definitely the pointer goes up to the top and take out the first instruction, and so you can run everything from the top and go back and forth like as a loop, right? For software, it's easy to understand, right? Because it take out that instruction and put it into the into CPU and do the computation, right? And then output the results to the memory, and then you can report it to the ports. That's how the software works for the CPU. But for hardware, it's already implemented. It's a piece of logic block. How is that being executed forever? If you look at this always block.
The inputs are always just mapping those outputs.
Uh-huh. Yeah, so you can see the always at, right? Always at something. You put the sensitivity list, which are the inputs for this case. But for the sequential design in the future, we are putting the rising edge or falling edge of the clocks in there. So that means it's actually being executed forever, because whenever that input or the whatever on the sensitivity list, if that one getting updated, it updates all the hardware's output. That's the way it's being executed forever. It's always updating. It's updating everything, updating the output of the hardware, the piece of hardware, instead of running the instructions from the instruction memory from top to bottom as a loop. Okay? That makes sense, right? It's just a piece of hardware. It's not, never think about the whole thing which are writing up in Vivado or Vim will be executed from top to bottom as the instructions. It's not, because these are hardware, not software. So once this is being synthesized by Vivado, it's like a picture or image or circuits, done. It's done on the chip. Okay? So the question is, are you able to write a piece of software for hardware in IPGA? I mean, all these are hardware. These are not software, right? If you're looking at what I'm showing to you guys, these are not software. Are you able to write a software for the hardware on the IPGA? And how? For sure, yes, right? Since people are, like the WDC IPGAs, they're converting their IPGA into a commercial microcontroller. It's not a dedicated ASIC fabricated by TSMC, but you definitely are able to design the hardware and a software associated with the hardware on the IPGA. So my question for you guys is how? You just do whatever the microcontroller has been doing, right? So the hardware is the same hardware as IPGA, but you have a block of memory that can be synthesized by your Verilog, and then you can just load your software to these memory instruction memories, and then the hardware you are designing, it just has the capability, has a CPU, has everything, has a pointer, is able to take out every single instruction from the instruction memories that you design as a hot piece of hardware, and then being sent to the CPU and run the computation for you. Doable, but this is not. This is just hardware, right? So we have let me show that really quick. We'll have two. It's called SoC. If you guys are not familiar with the term, I mean, sometimes knowing the terms is critical. I just shown that you guys are not a layman, right? So SoC is system on, and on has this O here has to be lowercase. System on chip, right? System on chip. So system on chips. These are the ASICs that has a system, for example, CPU and memories and ports. So the microcontroller is considered as a system on chip. It's not just a simple CPU. So the WDC microcontroller is system on chip, and we are going to implement two different platforms of system on SoCs. So one of them is going to be the one from the textbook. I'll show you. It's called Pico Blaze. And we call it the soft core. Where is it? Where's the soft core? It's up here. Soft core. So it's called the soft core because the core was implemented by a Verilog or RTL. You see the difference? It's a piece of digital logic, digital circuits that being described in Verilog, and you synthesize it and you implement it into RPGA. That becomes a soft core. A hard core is when a digital designer, when they design an IPGA chip, they optimized everything. They may even probably manually adjusted a lot of circuits in there, and they design their circuits with all the empty or LETs, in us, and send it out for fabrication. So this is a soft core because we have the RTL. We synthesize it using Vivado, and we were able to program it using assembly. Okay, let me show you one of the assembly code over here. Okay, so these are the processor's ports, for the test bench, and these are the assembly code. So the assembly code, because it's we're not designing a compiler for it. So eventually the code of the assembly code is being put into a Verilog code, and it's being synthesized into a .v file, and eventually we synthesize everything so that the instructions will be directly placed into LUTs. So this is the soft core. A hard core is a CPU that the digital designers, for example, here's a Z board. I showed you last week. That's a more expensive one, the Z board. It has an ARM core over there. So that ARM core is already fabricated, designed and fabricated into the IPGA. And you are not able to change it. So it's a hard core. This is a Cortex A9, I remember. It's from ARM. It's an ARM core. So that's why the Z board is more expensive, because they have to purchase the ARM core as IP and place it into the IPGA chip. And they're selling the IPGA chip with some hard cores in there already physically implemented into the IPGA with all the LUT units and interconnections as well. So you are able to modify design your customize the digital circuits in here and make interconnections with the core, with hard core as well. But for our Arctic 7 IPGA, it doesn't have any hard core in there except the ADC. So for our Arctic 7, We don't have a hardcore, but there is a little ADC over there. So you can design your digital circuits and make interconnections with ADC. Okay. Any questions on this? All right, let's come back to this one. And we do not usually use a sign statement in always block. Sometimes it works, but it's not considered synthesizable. If you are really implementing everything on ASIC, we do not use the sign like as whatever you use in the data flow method. You can see in always, if you want to assign something, just directly assign it, right? You don't really put a sign keyword in front of it. And for the behavioral modeling methods, when we use always at something, okay, if you see this is the past edge of the clock, even though we don't have a clock here for now, but the clock could be a simulation clock. You are just toggling a signal line in the simulation, or you could use a clock, a physical clock on the IPGA board. So the IPGA board has a physical clock. It's the physical pin, actually. It's 100 megahertz. Just let you guys know. There's a 100 megahertz clock. If you connect that clock from the test bench, which is the board, to your sub module, and it will be able to detect this signal, and whenever the rising edge arrives, it do all the updates within the sub module. So, like I said, 100 megahertz for the clock. Do you think it's slow or fast compared to Arduino's? What's the frequency of the Arduino's? Remember, we did 60 megahertz, right? So 60 megahertz compared to 100 megahertz, right? Like not 8, but 6, 7 times more faster than Arduino's. I don't know why the Arduino's are not able to run that faster, like 100 megahertz. And people are a lot of times they don't know how to program FPGAs, like for general engineers, but they definitely heard that, oh, you guys are playing with FPGAs, it's so cool because FPGAs are so fast. But we should know why, right? When we are telling people FPGAs are fast, we should know why. Why Arduinos are not that fast. There are so many reasons, right? So first, all these Arduino microcontrollers, they are based on super old architectures, and they are not being updated really often. They want to keep the cost low because these Arduino chips or similar microcontrollers are being used just for $10 toys made in China in Walmart, and they don't need to update it at all. They just use like 2 timers and 1 UART, 1 SPI at the most, interface with the sensor and running at 2 megahertz. That'll be good enough. They want to keep the cost lower than $1 per chip. So as long as it works for 40 years. They don't have to change it. Okay. Whenever they change any of the very mature architecture of the microcontroller, they have to recruit a full team of digital designers, chip designers that pays them $200,000 a year, and then do the verification, do the prototyping with TSMC again, and that'll be another $20 million. And eventually get a chip, probably it's not functioning, they have to do it for another year. So usually a cycle for making an ASIC like that takes 2 years. And you have to pay a group of front and back end designers to do it. And we know Arduinos are working, and for microchip, for the companies, they will just keep fabricating it with TSMC or a different company and just keep the cost lower than $1. If they do it again, probably the cost will be like more than $2, and they immediately lose the market to some other microcontrollers. So they do not really update the microcontroller architecture or circuits very often, and usually it's like 20, 30 years before they update anything on the microcontrollers. Because the Arduinos are probably like a 25, 30-year-old technology already. But IPGAs are different. Okay, IPGAs are different. So IPGAs are very simple, repetitive structure. They don't have IoTs and MUX. It's very simple. And whenever they decided to do a new product, they can for example, 10 years ago we were still talking about 28 nanometer technology, and now it's like 7 nanometer technology, and maybe 25 years ago it was 180 nanometer technology. So it's changing so fast. And for IPGAs, they are selling them at $7 to $10, And a lot of people, when they use FPGAs, they actually expect higher performance when they want to change to a new product, because they want to have their new ASIC design to be verified on the new hardware. So they would rather use a 28 nanometer technology launched 10 years ago instead of a 180 nanometer technology of the FPGA launched like 20 years ago. So FPGAs are being updated more often compared to microcontrollers. So you can see the RTX 7, these FPGAs like a basic 3 board. I bought it. It's pretty much already eight years ago. The second year I joined the college, but it was fabricated under 28 nanometer technology. By that year, it was really advanced, actually, 28 nanometer technology, and by far, I think 28 is still really popular, still the most popular one, because it's pretty fast, and also it's not that expensive compared to 7. But people who are doing the Apple or Samsung, the newest Snapdragon CPUs for the newest phones, they are probably using like 7 or 5 nanometer technology. But for these FPGAs, they don't really have to, because the cost will be a lot higher if you use the 7 nanometer ones. And the 28 is fast enough and is a reasonable cost. So 28 is still pretty good. And the reason that our FPGA can run faster than Arduino is because the FPGA we are using is a 28 nanometer based, and Arduino was 350 from 30 years ago. So the minimum size of the transistor is going to be 350 nanometers for the length. All right, but for our FPGA, all the transistor inside is 28. So definitely the power consumption will be lower. No, if you run it faster, the power consumption will be higher. But the thing is, it's running 1 volts for the core because the channel length is smaller, the threshold voltage is lower, and the Arduinos are probably 5. So the VDD is higher, so the power consumption is higher for Arduinos, and it's not able to run faster. So these are all the trade-offs between choosing different technologies for the certain products. So come back to the question: why FPGAs are usually faster than microcontrollers? So first, they usually use a newer technology, right? And their transistors are smaller, so they can run faster, and their VDDs are smaller, so when charging and discharging with a higher frequency, it's able to drive it compared to the bigger technologies like Arduinos. Another reason is for the microcontrollers, they want to keep it more general purpose. Microcontrollers, So for our microcontrollers, we have a lot of ADCs, a lot of other things. And like ADCs, they probably will cap the speed at a certain level. But FPGAs, it doesn't really have a lot of analog stuff in there, so it doesn't have to accommodate all the low speed blocks inside the FPGA. So most of the time, FPGAs are just a pure digital device. Okay? But microcontrollers are not, because microcontrollers are designed for general purpose devices, like toys in Walmart, right? Okay. If you look at this block over here, the first difference between blocking and non-blocking assignment, because there are 2 assignment types according to question number 3. So what are the 2 assignment types in behavior modeling? So there are 2 different methods. One is called blocking one, another one is called non-blocking. And to be able to use, sometimes it both works for a certain design, and sometimes it only works for a certain type of design. So you have to keep working on all these similar assignments that involves all the 2 different assignments throughout the semester to be able to use the correct one for certain circumstances. But you can see that the fundamental difference between blocking and non-blocking. So first you want to know which one is blocking, which one is non-blocking. So blocking is the equal sign. Non-blocking is the equal sign with the arrow in front of it. So blocking is actually blocks the execution from the next line before the first line is getting done, completed. So it's waiting for that line to be done, then it uses that result for the next one. That's called blocking, which makes sense because it's blocking the next one from being executed until the first one, until the current one is completed. That's called blocking, which the equal sign. Okay, so the blocking statement blocks the next line from being executed until the current one is completed. And non-blocking is different because non-blocking can see these 3 lines over here. It's not blocking the next one, so it's basically doing assignment from right to left at the same time. So what's going to happen is, for example, this always block always at the rising edge. So past edge is rising edge of the clock. So always at the rising edge of the clock, when the rising edge comes, right, it starts doing these one by one, boom, 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 and then all the 3 here will be executed at once. Okay. So for example, if x holds the value of 1, right, holds the value of 1, and after the rising edge of the clock, what the values are in y0, y1, y2. If x is 1. After the rising edge, what are the values over here? They're all 1s. They're all 1s. Because finishes this first, and y0 will be 1, okay? And y0 is updated and then assigned to y1, and y1 is updated and then assigned to y2. So all these will be updated because it's waiting for the one to be completed. So it's a blocking. Okay, it's a blocking. But for non-blocking, if x is 1, and just assuming that all the y's are 0s, right? After the execution here, after the first rising edge, what are the values in these? The first rising edge. Just let me know in the sequence, y3, y4, y5. What are these values?
3 will be 1.
Yeah.
4 will be 0.
Yes.
Or whatever it was before.
Okay. So what about the second rising edge? Because always, right? It's always. It's executing forever. So rising edge is coming always, right? So the first rising edge updated y3, and the second rising edge is going to update what? y4. Because y3 is already updated. So the second rising edge is going to update y4. So after the second rising edge, it becomes what? 110. And the third will becomes 111, right? So you need 3 clock cycles to give 1s to all of them. But for this one, for blocking, the first clock will give 1s to all these 3 positions. So one of the tasks of the tutorial is asking you guys to verify it in Verilog. So here comes the question: how do you create a clock? Right? How do you create a clock in Verilog? Okay. I mean, simply Google it. AI will just tell you. It's allowed here to use AI or whatever. Just do a search. How do you create a clock in simulation? It's very simple. It's just toggling one line here, and it's able to create it. You can put that sub module in the same module. I think this is a test bench, or no? It's a sub module. Yeah, it's not that difficult. Okay. So just verify it. Verify the blocking and non-blocking, and show the differences between these two. Okay. Let me see if I have an example over here. I probably have an example over here. No. You guys can search for that. Just learn how to learn from online resources. Okay. And number 5. In general, which assignment type should be used in combinational logic, and which assignment should be used in sequential logic? And so usually blocking for combinational and non-blocking for sequential. But there are many cases that are interchangeable. It's probably not absolutely right, but in general cases, blocking for combinational and non-blocking for sequential. So if you have a clock, it's going to be sequential sound.
Can you use blocking and non-blocking assignments in like data flow and behavioral blocks?
And these are, so for
Just
non-blocking,
for-
yeah, non-blocking is for behavioral in general.
Okay.
Yeah, I mean blocking is you have to add a sign to it if you are doing data flow. For structural, it doesn't have that kind of mechanism there. It's just a gate structure. So you can see in the future most of the cases whenever it's getting more complicated, 90% of the modeling methods are going to be behavioral because you just don't have the circuits. You have to see the circuits in order to do structural, right? And if the circuit has like millions of transistors, there's no way that it can do structural at all. Okay. Timing and delay, that's another big piece here. And we rarely model these rising edge and falling edge time delays, but the example after it will be critical since for simulations you do need a delay to expand it on the time domain. So you can see here is an example from the textbook. Okay, from the textbook. Oh, let's come back to the syllabus real quick and show you guys what the two textbooks are doing here. I didn't cover that yesterday or on Tuesday. So see that we have two textbooks, and most of the examples in the tutorials from this class is from the first textbook. That's why I put a required textbook over there. You can see it's, covers almost all the chapters from this textbook. I convert it into tutorials and implement on IPGAs. So that's how I designed this course at the very beginning. So that's the first textbook. And the second textbook is very popular, I'll let you guys know. And they don't have a dedicated version for Basis 3 because you can see it's being used on the Spartan 3 version. Spartan 3. I'm not sure it's using Arctic 7 or not, but it's a totally different platform. We could always look at their Verilog and convert it into the version that is compatible with our Basis 3 board. But this is a very good reference that shows you a lot of examples of standard digital modules like I2C, SPI, and everything, and especially the Pico Blaze. So the Pico Blaze is not, the soft core one is not included into this tutorial at all, but it's available for this in this textbook. So this is optional, but if you really want to get deeper into this area, I highly recommend it. But the first one is kind of a little bit required. But you can always find a lot of information from my online tutorials as well. I mean, it's not the end of the world if you don't have the textbook. Since I already put everything on my tutorial, but it's a good material to read actually as a reference. Just to let you guys know. And the second one is a really popular one. I didn't put a lot of materials from the site converted into my tutorials actually on my website. But I think especially for the soft core one with the Pico Blaze, you won't be able to find any information from the first textbook. It's always in the second one. Okay, just to let you guys know. Both of them are really good learning resources. Now let's go back to the time delay one. Let's see how the delay works for the simulations. You'll see a difference, a slightly different way of coding this up. So asterisk, hashtag, guys, is hashtag, followed by 20, followed by a number, and that number's unit is actually nanoseconds. Okay, nanoseconds. Because the time scale we put on the top with a 1 nanosecond as a time unit and 1 picoseconds as a resolution. So if you do put a number here, it's basically using the unit of 1 nanosecond. So this is creating a 20 nanosecond time delay, and then implement the logic. That's how that works. And sometimes you'll see that you simply just put a time delay and semicolon. So that means after that time delay, you don't really do anything. It just done. It finishes that line. Okay, so 100 nanosecond time delay and semicolon. So it doesn't do anything. However, you can see this doesn't do anything. It stops, just a pure time delay. And then repeat. You can see repeat. So repeat, parenthesis 4. And there's no semicolon over here. Even though I change the lines or the line breaker, but there's no semicolon, which means this is one piece of code. Repeat, no semicolon. It continues over here. Repeat this whole thing. Repeat this line. And stops at the semicolon. So it's actually a 100 nanosecond time delay. And then update the logic. So delay it first. And then run this update. So keep in mind that when you are plotting that, or trying to predict the results, you always extend the previous results with a time delay, and then this updates, it's just a one dot. I don't know if that makes sense. Because this logic assignment doesn't have a time domain, it's just one assignment. The time delay is right before it. So the time delay extends the previous result. And at the end of the time delay, there's just one update. If there's a change, it's going to change. If there's no change, it's going to keep at the point with the same value. So that's going to be a dot. So this assignment will be a dot at the end of the 100 nanosecond time delay. So when you plot it, make sure that you have the extension and then update it as a dot. So I plot it here for you to make it more intuitive, like this. However, I saw a little thing that doesn't match my prediction, but we'll run it later. We'll verify it pretty soon. We'll see what's really happening over there. But now for the first couple of periods, that matches our calculation. Okay, so let's see what's happening over here. I'll let you guys go through the two modules really quick first, instead of directly jumping into it. So first we can see it's a one sub module. This is the sub module here, right? It's called test one. Test one has 4 ports, 2 inputs, 2 outputs. And here's the logic. Output 1 is just a very simple combinational logic. Output 2 has an embedded 20 nanosecond net time delay, and then update it. Okay, it's just simply the inverse of input 2 for output 2. But output 1 is a combinational logic. And for the combinational logic, there's a precedence for the operators, and it runs AND and OR first, and then do the XOR in the middle, just let you guys know. I should have put a parenthesis over here to make it more clear, but just let you guys know, it runs, if you have all these operators, it actually runs AND OR first, and then the 2 results is being XORed together afterwards. Okay, so let's do a very quick calculation first. If in 1 in 2 are both zeros at the very beginning, L1 is going to be what? Immediately, right? So this is the compositional logic. There's no control in the middle. So if you have inputs are available as 2 zeros, and L1 will immediately give a result. And what is L1? 0. Okay? What about L2? When it got started, the first 20 nanosecond is going to be what?
0.
Is actually unknown, right? Because first 20 nanoseconds is delayed, so it's not actually running this for L2. So L2, you don't even know what L2 is because there's no function, logic function to control it. So the first 20 nanoseconds, you don't have a result unless you assign an initial value over here in your initial begin, right? And you have to assign L2 as a register type instead of a wire, right? I have to specify that it's a reg type. So it's able to hold the value. Otherwise, you are expecting for the first 20 nanoseconds, it should be unknown. So you can see I'm labeling, when I'm drawing this diagram, so in the future, there might be a quiz to let you guys draw the timing diagram according to the Verilog code like this, okay? We're just going through every single point one by one. So now, at the very beginning, from 0 nanoseconds, right? So we all know that initially in1 and in2 are both zeros. So that's why these are both zeros as a dot. We just plot a dot over there. And because it's a combinational logic, so out1 should be 0 as well. We just went through this assignment immediately at 0 nanoseconds. However, out2 is unknown, so that's why I placed a 20 nanosecond time delay over here as unknown. We don't know what out2 is. Until the end of the 20 nanoseconds, we know it. And what is it? 1, because the inverse of in2. And in2 is 0 as the initial value. So when you are plotting something like this, at least you can label 0 nanoseconds, you have boom, 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 3 dots. And for out2, you draw a time delay with unknown result, and then you draw a 1 over here. So this is what you already know. And what is after that, if you are looking at the test bench over here? So you can see the test bench is nothing but, you are bringing the sub module of test 1, and you name it as UUT. UUT is what? Unit under test. Because it's a test bench, just the unit under test. So in the lab on Tuesday, the name we had for the sub module was DUT. Remember, it's the device under test. Doesn't matter. You'll see UUTs, DUTs, whatever. You can name it whatever you want. Okay, and this is you essentially your sub module here and your initial design assign values for the test bench. And you'll see here, after assigning the values, I immediately give a 100 nanosecond time delay, right? Before I repeat this single line here. So what is this single line doing? Just want to zoom in and let you guys know, this is not a parenthesis, it's a curly bracket. Okay, similar to this one, it's a very important technique to be used in Verilog. So the curly bracket being used here is used as a concatenation. So you can put 2 signal lines and combine them as a 2-bit binary number. So in1, in2, these were individual lines. So these were single binary numbers. But to do the concatenation in this format, it becomes a 2-bit binary number. So in1 here becomes what? If you have a 1 here, it becomes what? 2. So this was 0, 0, and you had a 0, 0 plus 1, it's going to be what? 0, 1. So you are basically adding a 1 to the 2-digit binary number. So every time you add a 1 starting from 0, 0, it becomes 0, 1, and then 1, 0, and then 1, 1. And then cycle back to 0, 0. That's what's happening here, okay? But however, every time it delays for 100 nanoseconds before it updates the two digits. Okay? So now let's come back. And this will be repeated for 4 times, just to let you guys know. Okay? The first time, this is 0, 0, right? 0, 0 plus 1 becomes 1, 0. That's the first time. Second time, So first time 0, 1, second time 1, 0, third time 1, 1, and the fourth time will come back to 0, 0. That's all you have. Okay? And if we look at our inputs, let's see if that makes sense. Remember at the very beginning I had these 2 values to be 0, 0s. Okay? And immediately I got a 100 nanosecond time delay, no matter what. So just draw a 100 nanosecond time delay and don't do anything else because it's not updating anything after this. Right? No dots. No dots. Why no dots? Because just a 100 nanosecond time delay with a semicolon, it ends it without any updates. So it's no dots. and then get into the repeat statement, and immediately followed by another 100 nanosecond time delay. Right? Before update the two inputs. So followed by another 100 nanosecond time delay. So it extends it. Alright, okay? And then update the two inputs. Remember, it jumps from 0, 0 to what? 0, 1. So you put a 1 to in 2. But input 1 doesn't change. And input 1 adds a 1 to it. So it just directly plot a dot over here for in 2. Because of the concatenation, remember? Because of this guy. Okay? It does this. And after that, it becomes very simple. Because for the inputs, it's just simply repeating. 100 nanosecond time delay, update it, 100 nanosecond, update it, right? So just keep doing it. 0, 1, 1, 0, 1, 1, 0, 0, done. Make sense? So you can get the inputs done easily. Now let's come down to the outputs. Outputs a little bit trickier. Okay? Since you have the inputs, and you know the logic, you can definitely plug in the input values into the logic functions and find out the outputs. Right? Okay. Is output 1 being delayed? No. Is output 2 being delayed? Yes. Okay. So it's combinational logic. Once inputs are being updated, output 1 will be updated. Is that right? And there's no time delay. So let's just use this logic function here and plug in all the inputs and find out output 1. Does that make sense? Okay. Look at the logic function for output 1. And or XOR, okay? So if you have 0, 0, output 1 is what? 0. Okay? It stays at 0, so it's not changing. Until here it changes. I got a 0, 1. 0, 1 for the inputs. You got 0, 1, right? So this becomes 0. This becomes 1. And do an XOR, it's going to be 1. So that's why output 1 is getting updated.
The way that's written, would it not execute in 1 and in 2, and then the XOR, and then the OR?
No, it's a precedence of the operators. You can refer to a reference here. You know, based on this, it's actually, you see, it has to run and or first before it runs this, right?
Those part of the same way.
But that might be the issue. You know what I mean? I'm gonna go to the second one. You'll see.
Can you just use parentheses?
It's better to use parentheses actually. So for this class, as in the class, I mean, when you guys are running this one, please add a parentheses to these two groups. Yeah, this is the example from the textbook. It doesn't have parentheses, but and you cannot always trust the textbook. I already picked up probably 10 errors from the textbook for all these like 12 tutorials. So let me see if they have a. I don't know if they are doing. I don't remember what was the intention. Are they trying to do it sequentially or trying to follow the precedence over here? But just let you guys know, if we keep going, we see a little difference which doesn't match our prediction. It probably is because of the parentheses over here. So when you guys do the assignment, please show me what's happening over there. Okay, so the first one is still working, right? So the 0, 1, 0, 1 is giving you 1, and 1, 0 is also giving you a 1. However, 1, 1 is not matching our prediction. When both of the inputs are 1, 1s, if you are doing this, and XOR will be a 0, but still showing a 1. So let's see if we do this. If we do a 1 1, it's going to be 1 1 0 1. So that matches actually. If you do it sequentially. Let's slow down a little bit. Tell me if that makes sense. So now both the inputs are ones. Both of the inputs are ones. If you do this AND logic first, it becomes a 1. If you do this one second, it becomes 1. And then you do XOR, it's 1 XOR 1 because both are the same. So for XOR, it's outputting a 0, right? But actually, it's not 0. It's a 1. How I know that? Because I did run the simulation here. See? 1 1 is a 1. It's not a 0. Okay? However, if we follow the sequence, like what Luke just suggested, it's going to be AND 1 is 1, right? And 1 XOR 1 will be 0. And 0 or 1 will be 1. And that works. And that might be how it works, actually, how it's being executed in Verilog, in Vivado. Because I directly used the code, I didn't change it. You can see these are the code over here in Vivado. But that's good to know. But according to the operator's precedence over here, you do AND first, do OR first before it runs XOR. Or maybe these are in the same level when they put everything in the same block. I think that's the case, actually. Do you agree with that? So if they put everything, put all the operations in the same box, actually they have the same precedence.
I think so.
So it's just left to right.
Yeah, left to right. Yeah. Okay. So only parenthesis has a higher level here, right? It'll run first, but all these ones are the same priority here. And then that will match our result. So that's for output 1. What about output 2? Seems a little bit trickier. However, you just keep in mind that it's doing nothing but just adding a one more 20 nanosecond delay before it updates, right? Since we know that over here we already know it's 20 nanosecond delay and then a 1 here, because the inverse of in2 and in2 was 0, so that's why it's a 1. And whenever everything here, whenever output 1 updates, you want to wait until the end of the 20 nanoseconds and then update it. That's the only difference. It's actually really simple. So it's just looking at, so when you are plotting output 2, you are only looking at in2 because it's inverse of in2, right? Okay? So look at in2. Okay, in2 changes. I don't want to change immediately. I add a 20 nanosecond delay and then change it. Okay, keep going, keep going. Okay, in2 changes. I don't want to change immediately. I add a 20 nanosecond delay and change it. Inverse, put an inverse over here. And then keep going, keep going. Okay, in2 changes again. Let's wait for 20 nanoseconds and then change it. If you're comparing L2 to in2, it's basically just a 20 nanosecond shift to the right. So the signal is the same. No, it's the inverse of in2, but 20 nanosecond shift to the right. That's it. That's the only difference. It's the inverse, but wait for 20 nanoseconds and then invert it. Okay? So I have a similar problem on the quiz next week. Would you be able to plot it by hand? Just study this, is recorded. Just study it, all right? Number 6. So we are getting into a different way of modeling a digital design. Oh, before we do that, look at this one. So that's a simulation. See, this is unknown. This is showing unknown results for output 2. Okay, just let you know. And another modeling method is called hierarchical modeling methods. It's not very different from a behavioral or the other methods. And just using a hierarchical modeling structure. It's not any differences on syntax. It's just a different methods. It's bringing more submodules into the top and making interconnections between the submodules. So there's one thing we want to look at, which is how do we make connections between the modules. I think there's a better example up here instead of using that one, I think. Let's see. Here. Okay? Dot something, parentheses, comma. Dot something, parentheses, comma. So what is this? What is this? Keep in mind that when you instantiate a submodule in your top, right? So the syntax of doing that is you put a submodule's name here, you rename it in your top, and immediately have a parenthesis and dot, okay, dot, and port. That port, the port following that dot, it's going to be the port of the submodule, not the top. So we are looking at the example on problem number 6. You can see dot A. So we don't have the half adders module included over here, but we do instantiate it in the top module of this example for problem number 6. Okay, and you'll see it just have a line breaker in between different the different lines. There's a dot A, right? Dot A input underscore A, comma, dot B input. So by doing it in this way, it's just making it super clear about what are the ports is being connected to the top. And keep in mind that the port right after the dot is the port of the submodule, not the top. You can see the top also has a lot of ports, right? 4 ports. Input underscore A, input underscore B, input underscore B, and output underscore sum, output underscore carry, right? So these are the top ports. But the half adder as a submodule, its ports are A, B, sum, and carry. So following this question, I immediately have a number 7, asking you guys to handwrite the half adder module using these port names. Please start doing so right now, and using 3 different modeling methods. We probably have to do the quiz next time, but let's try to finish it in class as much as we can. So now I'm going to give you time by looking at the schematic of the half adder, okay, and use 3 different modeling methods and the correct port names indicated in problem number 6 to form the half adder in Verilog. Keep in mind that the model name has to match with whatever being instantiated in the top, and has to be half underscore adder or lowercase, right? That's the name of it. So for your module names, if you have a different module name, you use a dash instead of a underscore. If you use uppercase, it won't work. I'm gonna deduct points from you guys. Okay, so make sure you use the correct names. You know what I'm saying? Now we are working on that problem number 7. Problem number 7. Make sure you have the correct port names and correct module names.
I wrote all the port names abbreviated. Should I clarify it or rewrite every variable that I wrote?
I mean, the port names has to match with the whatever in the top.
Yeah. Could I clarify that that's what it's supposed to be, or should I erase each one and rewrite it?
You just correct it. Just correct it into the right ones.
Okay.
Mm. and you don't need a wire, right? Because the ports are directly connected to the inputs and outputs are directly outputs. You don't have intermediate signal lines and don't use wires. So I saw these issues from the in class 1. I deducted 1 point for you guys if you did a wire over there, I think. That's a little feedback from the in class 1. So please don't do that. And anything else I saw.
I didn't realize you gave us this space.
No.
I did it before, and so that's why I abbreviated each one. Should I rewrite all of them like this?
No, it doesn't matter this guy or not because all the ports names are right here,
Right.
right? So you just have to use AB sum carry for this, and I have to use this one for the module.
Oh, so I don't have to use input or output sum or output carry. I can just use carry. Oh,
These are outputs. These are outputs. So these are outputs. These are inputs, right? So you just have to, the name has to match.
like this part, or
No,
just this part.
these are the sum modules, right? And now you are designing your sum module. That's why these has to be in your sum modules ports, and these are the tops ports.
Okay.
That makes sense.
Yeah, that does make
Yeah.
sense.
So this is just showing the logic. So you can use the logic here, right?
Okay.
Actual and right. So you use the logic,
Mhm.
but the names are already providing here.
Okay. And so then. Okay, yeah, that makes sense.
Mhm.
Thank you.
Cool. And I'll briefly talk about problem number 8, and we'll give you guys the time to work on it until the end of the class. Okay. So number 8 is easier. It's just telling you that sometimes you see examples online. It doesn't show you that little dot over here. You know what I mean? So if you look at the problem, so it shows you example there. My design, right? So let me open it up, just in case you don't have it. Okay. So you see when they instantiate a sum module here, and they put the ports dot the ports of the sum module and parentheses the ports of the top. So this is the way they make a connection, right? So which means this port is connected to the top's port A, so on and so forth. So this is highly recommended, and we should always code it up in this way. But we'll see a lot of examples. They didn't do anything about the sum modules port. They directly just write down just list all the ports of the top. For example, here, this module. See? Instantiate my design, which is sum module, and name it as D0, device 0, or whatever, and parentheses A, B, C, D.
When you start that module, you say module TB underscore top and then the colon.
Semicolon here?
Yeah, the semicolon.
Yeah, because this is a simulation top probably, so it doesn't have ports. Yeah, yeah. But that's not important for this example, though. I mean, this is showing you. So this is a module, right? A module called my design. It's a digital block, has inputs and outputs. So the inputs are X, Y, Z, 3 inputs, and 1 output is O. Okay, that's it. Just black box, whatever, AND gate, whatever, three input AND gate, whatever. So 3 inputs and 1 output being listed like this, and then you trying to write up a top simulation module. It's a module top, and have all the wires declared, and then you instantiate my design into your top, and then name it as D0, and then you are trying to make connections between the top and the sub module. And I directly list A, B, C, D without telling you like which is connect to which. Like this. Nicely, right? So A dot A connect to input A. So you are making connections. So the simulation signal from input A will be put into A of the sub module. But here is different. Here it doesn't have that dot thing. It directly lists A, B, C, D. So in this case, the method here is being used is called positional association. Positional association. So in this case, order matters. Order matters. So you have to go back to the sub design, the sub module, to look at the order. So the order being declared, or the ports being declared, is XYZO. XYZO. And when you do the ports and trying to make the connections using positional association, and when you are not including the sub modules ports, if you directly put ABCD here, and these ABCD ports are the TOPS ports, keep in mind. It will be on the quiz in the future. So these are the TOPS ports. And they are being connected to the sub-modules ports in a certain sequence that being used in the sub-module. Like here, XYZO, and even though it doesn't tell you, but it's actually A connect to X, B connect to Y, C connect to Z, and D connect to O by default. And this is called a positional association, which is highly unrecommended. But you'll see this in a lot of different places, so you understand what's going on. Okay? And the first method, like the common method we should use, is called a named association. So you can see the sub-module's name, the top module's name, and the connection between these. All right. So problem number A is asking you to rewrite the top module in problem number 6 of the snapshot provided with you using positional association method instead of the named association method for problem number 6.
Can you assume that the positions of those are the correct ones for the non-existent half-adder module?
It's from top to bottom. Oh, whatever you used for your HA. Right? So your HA for problem number 7 has to match the order in problem number 8. Okay? Any questions? Anything? We still have 10 minutes. Any questions? Feel free to ask. So we'll do quiz 1 Tuesday next week.
Do you need these stapled together or no?
I'll do it for you. Don't worry about that. Oh, you can do it. Sure. Yeah.